Hello, everyone. Today, the topic of my study is validation of the overset mesh technique on roll damping of ships side by side. I will first introduce some definitions. First is the roll damping. As we all know, there are 6 degrees of freedom for a ship. However, among them, except roll motion, they can easily predict using a potential theory. But for roll motion near resonance, the roll amplitude are mainly controlled by some viscous flow separation. In this way, potential theory may fail to predict its roll amplitude, particularly. So we have to search for other options. Except the computational flow dynamics, also called safety, it can predict the roll motion in any circumstance, or in most of the circumstances. Those other techniques like semi-empirical have many restrictions. And in our study, we focus on the viscous component, the eddy making and BLGQ component. And then the side-by-side offloading. For the LNG for the large floating LNG platform, they have to offload the LNG. They have to offload the LNG to the LNG carriers. So this will bring 2 challenges. The first is to operate in open seas, which means more uncontrollable wave condition. And the second one is the offloading arms of the LNG will restrict the gap widths between 2 vessels, and usually this is less than 4 meters. Consider the geometry of 2 giant vessels. The gaps can be relatively small. And in that circumstance, if the roll motion are large, it may lead to the collision of the 2 ships. So roll motion becomes an important criteria for the safety of the side-by-side offloading operation. And to simulate the roll motion of side-by-side scenario in safety, we need to find a correct dynamic mesh technique. To make sure the sail quality can be preserved, the sliding and overset mesh are 2 potential options. And for sliding mesh, once the sliding interface is determined, the distance between the sliding interface and the water line on the hull, they determine the smallest possible gaps. This may not be an issue for hull with a relatively large beam drift ratio. This smallest possible gap is small, but for the aspect ratio are relatively small, the smallest possible gaps may be large. So this may not be so this restricts the application of sliding mesh to small aspect ratio cases, and that may not be our problem for overset mesh. Since the solver of the overset mesh will ultimately block those cells that are outside the computational domain, so it can be applied to cases of small aspect ratio. And what is overset mesh? Overset mesh is 2 things: simplification and communication. The overset mesh is invented to make the generation of the mesh simple. It is a mesh that's around the object you interest, so it will moves on the background mesh. And as long as the surface or the whole of the object do not outside the computational domain, they can work smoothly through the communication of the two meshes. And this makes the coupling of the meshes important. So the key things for the one of the key things for the overset mesh is to find the proper way to interpolate between two meshes. To reduce and this interpolation will inevitably bring in some errors. And to reduce these errors, we can choose high order mass conservation interpolation schemes, or we should make sure the cell size similar between regions and the interface. Or we need to place the overset interface far away from where the variant is large. But that may not be possible for side-by-side scenario. If the widths of the gap are extremely small compared with the geometry of the LNG carrier, we will have to set the overset mesh really close to the hole, which makes the vertex shading have to across the interface of the overset mesh, which conflicts the third guidance. And we have no options, even if we set a relatively large overset mesh. As we've mentioned, if the mesh cell sends outside the computational domain, which beyond the wall, they will be blocked, which makes the interface close to the hole anyway. So we have to evaluate this effect. So we set an experiment of both small and large overset mesh. Their background mesh are the same. And in fact, except the widths of the coverage, all those settings are the same. And since we use a submerged cases, we get rid of the effect of the wave component, and we provide a sharp corner, which makes the vertex component the dominant component in these cases. And this is the result of the roll moment, the time history of the roll moment. We set large and small overset mesh. Sorry, this is small overset mesh. And we choose different time steps for large, medium, and small. And we can see there is a small trend for there is a convergence trend for the small overset mesh as the time steps decrease. And the roll damping sufficient of the large and small overset mesh are quite similar. And let's say let's direct compare the large and overset mesh using the same time steps. As we can see, as time steps decrease, it seems the time history of the roll moment of two different mesh are closer to each other. And for the smallest time steps, we can see the vertex contours are similar. And also the pressure distribution on the vertical wall. And since for those fully submerged cases, it's hard to find an experiment. So we have to try the isolated cases and we have to consider the effect of the free surface. And then we compare our results with that of Reynolds-Young. And the time history of the experiment and numerical method fits quite well, except it seems our numerical results are are larger compared with that of Young. And so does the roll damping sufficient. It seems our results, since I use a very small overset mesh, it seems our results overestimate compared with the results of others. But that's not the case. If we look at those data more closely, the result of fluent and overset mesh are in fact conducted in recent 5 years, and those smaller results in all the frequencies, like the result of Reynolds-Young, where the numerical and his numerical results and the numerical results of the NAS2D they are done by at least 7 or 8 years ago, which means in the recent computational numerical results may spend more computational resources. So I don't think the small overset mesh overestimates a lot. So it may not be a big issue. And then for the side-by-side scenario, we choose to compare with since there is no, right now there is no experiment result, we have to compare with some numerical results. And we choose the beam drift ratio of 5, which makes it can directly compare with the sliding mesh. And the difference between the roll damping sufficient, it seems it's ripples. The difference is ripples, not waves or tsunami. And let's compare the vertex contour of the first point. In this picture, from the leg left to the right, the width of the gap keep increase. For the widest cases, we can consider it as isolated cases. And let's say the vertex contour of the middle picture, the side-by-side scenario with the narrowest gap. It's clear that compared with the isolated cases, the red vertex is relatively small. And we can see from the velocity of the field, it seems the vertical wall restricts the velocity in this area. But for the isolated cases, it's clear that the velocity in this area is much larger compared with the side-by-side scenario. So those restrictions, as we've mentioned, the vertex component are the main component for the vertex for the roll damping, and this may explain the decrease of the roll damping sufficient. So at this stage, we validate the overset mesh, and compared with previous study, we use extremely small overset mesh, and compared with previous study, they usually investigate, they usually compare their results using integrated data, but we focus more on the flow physics, like the vertex shading. And even though our previous results shows that the difference of the errors brought in by the interpolation of the overset mesh may be ripples, but we have to understand how large the ripple is, and we have to evaluate errors and uncertainty of this technique. Despite the application on roll damping or the shift motion, the overset mesh can also be applied to optimization, as it has been used in aerodynamics. We think these techniques can be applied to design more efficient wave energy converters, since it can make the background mesh similar and only change the overset mesh. So we can test different objects, a series of objects with independent overset mesh, and we can obtain a better performance wave energy converter. And that's all. Thank you.
Yep, thank you very much. These very exciting results, actually. We have 2 to 3 minutes for some questions. Are there any? Okay, so I have actually one, actually a few, but we don't have time to go through all.